Now we can start with Professor Alexander Vilenkin and talk about internal inflation and the beginning of the universe. So please, the pointer is there.
Yes, thank you. It's a pleasure to be here. In this talk, I would like to discuss the multiverse scenario, which has emerged over the last several decades from inflationary cosmology. And according to this scenario, different distant parts of the universe are very different from what we see around here, and may even be described by different laws of physics. And a question that has been debated over about the same time is whether or not this scenario can be tested observationally. And this is something I'm going to discuss here as well. And finally, if time permits, I will discuss also the implication of this picture of the universe for the question of whether or not the universe had a beginning. So first, before I get into this, I would like to briefly review the theory of inflation. So inflation is a period of very fast, accelerated expansion of the universe. This expansion is, the acceleration rather, is driven by a high energy false vacuum. And I'll say something about what exactly it means. When we say vacuum, well, vacuum is what you get when you remove everything that can be removed. So it is just empty space. So I tried to depict it here. And for a physicist, though, the vacuum is very different from nothing. It is endowed with energy and pressure, and also can exist in different energy states. Physicists refer to these different states of the vacuum as just different vacua. So particle physics models generally predict the existence of a number of vacuum states with different energies. And the lowest energy vacuum is called the true vacuum, this is a stable state, and all high energy vacuum are unstable and eventually decay, this lower vacuum. So let me just list the properties of a false vacuum. False vacuum, any vacuum which is not the true vacuum, which is not the lowest energy state, a false vacuum, because they are unstable and eventually decay. So let me list the properties of a false vacuum that are relevant to us. First of all, it has a high energy density, denoted here by rho, and it has an unusual property. If the universe expands, the density of matter goes down because matter is diluted, but vacuum is not diluted. The energy density of the vacuum is constant. So a cubic centimeter of space always has certain energy due to the vacuum. All right, so this is a constant. Also, vacuum has large negative pressure. Positive pressure is what you have in a balloon, which pushes outwards, and negative pressure is something that pushes inwards. It's like stretched piece of rubber, has negative pressure. And the exact relation is pressure equal to minus energy density, and it is a consequence of special relativity. So it's a consequence of relativistic invariance. The most important property of a false vacuum is its gravity. In general relativity, gravity, or roughly, the force of gravity is determined by this combination of energy and pressure, rho plus 3p. So in normal objects like stars, pressure is positive, and pressure only increases the gravitational attraction. But in the case of a vacuum, this P is equal, pressure is equal to minus rho, and this combination is negative, which indicates that vacuum is has repulsive gravity. And this applies to any vacuum, including ours. So finally, if you have so these first three properties apply to any vacuum, but the last one, if you have a high energy vacuum, which is false vacuum, it eventually decays, and it decays into lower energy vacuum, and the excess energy goes to create a hot fireball of particles and radiation. And this is what has probably happened during the Big Bang, according to this theory. Okay, so now we know all we need to know about false vacuum. So this theory of inflation assumes that at some point in the early history of the universe, the space was filled with false vacuum. You don't need the whole space, you need just a tiny bit of space to be filled with false vacuum. And then because of this repulsive gravity, it starts to expand and expands with acceleration. So the expansion actually turns out to be exponential. And in a tiny interval of time, this initial nugget of false vacuum becomes much bigger than the entire observable universe. So this is what is called inflation, cosmic inflation. Economic inflation is described by the similar law, exponential, but it is in a different time scale. So this, the reason we are interested in this scenario is because, as it was suggested originally by Alan Guth, it explains some puzzling features of the Big Bang that had to be postulated initially without explanation. In particular, it explains why the universe, the observed universe on the large scales is so homogeneous. The density of the universe is nearly the same on large scales, and also why the geometry of the universe is nearly flat. That is, the sum of angles in big triangles adds up to 180 degrees, although general relativity allows it to be anything. Also, even though the universe is predicted to be homogeneous, on average, there are small density fluctuations which later evolve into galaxies. And that you necessarily need, because we know that the universe is strictly homogeneous with structures. Okay, so this is basically outline of the idea of inflation. And originally, when it was suggested about 40 years ago, it was just a speculative hypothesis. But by now, we have a very impressive observational support for this theory. So for one thing, the main support comes from observations of the cosmic microwave background. This is kind of the afterglow of the Big Bang of this. Yeah, the role of Big Bang in this theory is played by the decay of false vacuum. When this hot mixture of particles and radiation is produced as a result of the decay, that's what we call the Big Bang. And as the universe expands, initially this mixture is very hot, but then cools down. And now we see a faint afterglow, which we call cosmic background radiation. And this is, this is the this picture of the intensity of radiation on the celestial sphere, and different colors correspond to different intensities, and variation between different colors is 1 part of 10 to the 5. So radiation, but with tiny variations, which show these initials. So we see the picture of the universe at a very young age, and all these inhomogeneities, which are very tiny at this time, later evolved into cosmic structures like galaxies and clusters. So then, when we we can take this pattern and expand it in spherical harmonics, and we get oops, oh, wait a minute. Yeah. So we get this picture, and this green line is what the theory predicts that we should see, and the red dots is what we actually see. So I would say that the agreement between the theory and observation is spectacular. And also, the theory of inflation predicts that the universe should be nearly flat. And indeed, measurements of huge triangles in the sky show that the large-scale universe is flat with at least 1% error. Given this data, by now inflation has become a leading cosmological paradigm. Now, if inflation is supported by the data in our parts of the universe, in our part of the universe, we should give some credence to what the theory tells us about how the remote parts, what they look like. So let's discuss what the theory tells about it and whether or not we can check it by observation. So what the theory tells us is that even though inflation ended in our local region, which happened some 14 billion years ago, this is our Big Bang, it still continues in remote parts of the universe. So in this sense, inflation is eternal. It never ends in the entire universe. The reason for that is that the end of inflation, this decay of false vacuum, is a quantum probabilistic process. And it doesn't happen everywhere at once. So it happened here, but in other parts of the universe, it hasn't happened yet. So that's the picture. Exactly how this decay occurs is somewhat model dependent, but the conclusion is not. Well, I should say that you can construct models of inflation which are not eternal, but that requires some designer model. So, sorry. This eternal character of inflation is a generic feature, although you can construct some models which are not eternal, but they require some unnatural features which I think are not attractive, but that's of course a value judgment. So this, as I said, decay of false vacuum occurs differently in different models, and I here focus on one kind of models, although the conclusions will not be different for a generic kind of other models. So here in this cartoon, this yellow background is the false vacuum. So you can imagine that it expands very fast in all directions. And these green bubbles are bubbles of normal, quotes, regions like ours, and they spontaneously pop out and immediately start to expand. All right, the bubbles expand very fast, but this inflating vacuum that separates them expands even faster. So bubbles are actually driven apart by this inflationary expansion, and that creates space for new bubbles to form. So this process continues forever, right? So this is one kind of realization of eternal inflation. And as it continues forever, an unlimited number of bubbles will be formed as the universe evolves. So here, I painted all bubbles green. so suggesting that they have similar properties. But particle physics models generally, as I mentioned, predict the existence of a number of different vacua. And generally, all kinds of bubbles filled with all different kinds of vacua will be formed. These bubbles differ. Basically, the physical character of our world is determined by what we call the constants of nature. These are like masses of elementary particles and strengths of their interactions, like gravity. So Newton's constant is one of the constants of nature. These different bubbles will have different values of the constants of nature. And for that reason, the physics there will be very different and maybe dramatically different. So this is what we call the multiverse. Now, a grand unified theory, like the kind of theory that was popular in the 1980s, predicts like a several vacua, for example. A small number, typically less than 10. Then you will have a few types of bubbles here. String theory, which now is arguably the best candidate for the fundamental theory of nature, but again, this depends on who you ask, predicts a lot larger number of vacua, like 10 to the 500. And the reason for this huge number is that string theory and a whole class of other models, like supergravity models, they require that the universe should have extra dimensions. So in addition to our 3 dimensions, the space has more dimensions, like in string theory, the total number of dimensions is 9. And then these extra dimensions, we don't see them, so they have to be curled up to a very small size. This is like a straw, right? A straw has large dimension and the small dimension, which is curled up. If you have not 1 extra dimension by 2, you can curl it up in a donut, in a pretzel with 2 holes, in something with 3 holes. So there are many ways you can curl up 2-dimensional space. But in string theory, you have 6 extra dimensions, and the number of possibilities of curling them up is combinatorial, and each way of compactification of this curling up corresponds to different values of the constants of nature, so the different vacua, right? So there is a good reason why these huge numbers come up. And then if you imagine that our universe is filled with bubbles with this many different types of environments, can we tell in what kind of bubble are we going to find ourselves? Most of these bubbles will probably not be suitable for any form of life, but some will have values of constants close to ours, and maybe something similar to what we have here will occur. Or maybe in some very different environments, you can have intelligent beings as well. Okay, so the question is, can we test this kind of theory observationally? So this picture, as I'm arguing that the picture that kind of shown in this cartoon is a natural outcome of the theory of inflation plus theories like string theory or other higher dimensional models which have some motivation for them. Some people believe strong motivation. So can this be tested observation? Well, some prominent cosmologists emphatically say no, And this includes George Ellis, David Gross, Rees Mollin, Paul Steinhardt, and a long list can be continued. They go as far as saying that these models are unfalsifiable and therefore, according to Popper, unscientific. Chris Mink gave a more measured criticism of this kind of models, and he says that they maybe not providing evidence for the underlying theory, but they can serve as consistency checks. And then there is at least not a smaller group of theorists. Some of them are no less distinguished, who strongly believe that this kind of theory can be tested. So this is the question I would like to address now. Sorry, I keep forgetting about this thing. The way we can try to test this theory is to try to predict the values of the constants of nature that we can expect to observe in our local region. Right? We cannot, all these different bubbles are beyond our horizon. So we cannot go there and measure the constants there. All we can do is to measure what we have here. Now, the standard model of particle physics has about 30 parameters. Unfortunately, most of them have already been measured. So there is very little left to predict, but there are some parameters that are not yet known. I would like to talk about, as an example, about the parameter called the cosmological constant, which has been measured, but it was measured not so long ago, about 25 years ago. And we can imagine going, and actually its value was predicted before that. So it can be argued as a success of this kind of anthropic prediction. So how do we address this question? So we cannot go to other regions, as I said, and measure there, but what we can say is the following. We can imagine that we have this picture of the multiverse with observers living in different bubbles. Most of the bubbles are barren, right? So because physics does not allow the existence of life, but there is no one there to complain about it. So only the populated bubbles will have some observers. And what we can do is to assume that we are typical observers in this multiverse. And if we can use the theory to calculate the probability of different values of lambda to be measured by a typical observer, then we can say this is, we don't know which of these observers is us. So that probability distribution should be identified with the probability for us to measure a given value of lambda. So this line of reasoning was originated by Brandon Carter, and he called it anthropic principle. Now, I call it a principle of mediocrity because basically the idea is that in some of the bubbles you have lots of observers. Some of the observers who are typical, there are large numbers of them, but there are also some rare observers which live in some very special circumstances. So if you think of us as being typical, then, or mediocre, then we should identify with these most numerous types of observers. Now, this formulation given by Nick Bostrom, it says that we should reason as if we are randomly picked in an appropriate reference class of observers in the multiverse. So what is added here is the reference class. So we are not just picked among all observers, but we should specify the reference class. And this is an important point. For example, if we want to address the probability distribution for lambda, lambda is what is used notation for the cosmological constant. We know and we imagine that now is 1995. We don't yet know the value of lambda. But we know pretty much all other constants of nature in our part of the universe. So then the appropriate class, reference class, is the class of observers who measured all the same values of the constants that we have here, other than cosmological constant, right? So we only then specialize on bubbles which have the same values of all the other constants except lambda. And the goal is to find the probability distribution for lambda in such bubbles. So the cosmological constant is a very interesting quantity. And before discussing how we can calculate this probability distribution and try to compare it with the data, let me give a brief introduction to lambda, because it was the understanding of the value of this constant is plagued with huge puzzles, which the best minds of theoretical physics have been struggled with for decades. So let me tell you what the puzzles are. The cosmological constant is the energy density of our vacuum, one we live in, right? It's not zero, but it is very small. Now, why there should be a non-zero energy density? Because due to the quantum processes, particle-antiparticle pairs are spontaneously created and destroyed constantly in the vacuum. And this process contributes energy to the vacuum, these quantum fluctuations. But then when you try to calculate what the magnitude of that energy be, say per cubic centimeter, you come up with a ridiculous answer. This lambda turns out to be 120 orders of magnitude greater than the density of matter, average density of matter in the universe. So if lambda were this high, the universe would be inflating like crazy. So that is obviously not the true value of lambda. Now in the 1990s, observations were performed, and we now know what lambda is. It is about twice the matter density. So this prediction, which is off by 120 orders of magnitude, has been often referred to as the worst prediction ever in theoretical physics. So and this is called the cosmological constant problem. Why is lambda so small? Well, one point that was noted by many people, that fermions and bosons, particles, contribute with opposite signs to energy density of the vacuum, and in principle these contributions would cancel out. However, you need cancellation up to 120th decimal, and this is a bit too much to ask. Okay, so this is called the cosmological constant problem. And there is another problem. Another problem is that you notice that lambda is about twice matter density. So these two densities, energy densities, are comparable to one another. And this is very puzzling because if you ask how these two densities behave with time, as I mentioned before, vacuum energy density remains constant. So in this graph, you see lambda remains constant with time, but matter density decreases with the expansion of the universe. So at earlier cosmic times, matter density was much greater than lambda, and in later times it will be much smaller than lambda. So why is it that we happen to live at this very special moment in the history of the universe when the two densities are comparable to one another? So this is called the coincidence problem. Okay, so as I said, physicists struggled with these problems, and the multiverse picture offers a solution. Some people are not satisfied with it and are still struggling with these problems. So let's discuss what happens in the multiverse. So the first take at it was made by Steven Weinberg. This is the picture that we have. We have different kinds of bubbles. Lambda takes different values, and these values range of 120 orders of magnitude. In these bubbles, as I mentioned, if you imagine they had some big bang and then matter density went down. So what happens is that when the matter density is much greater than lambda, you have ordinary gravity. Because remember, lambda, vacuum energy is repulsive. Vacuum is gravitationally repulsive. So when matter density is much greater than vacuum energy density, this repulsive gravity is dominated by attractive gravity of matter, and this attractive gravity causes galaxies to form, and structure formation in the universe goes on schedule. But once you reach this point, this time, when matter density goes below lambda, gravity becomes repulsive, and structure formation stops. If lambda is very large, if you imagine that this line goes like right there, this point may happen before any galaxies had a chance to form. So if lambda is too large, you will have no galaxies at all. And this is what was Weinberg's main point. So he pointed out, he calculated that if lambda is greater than 1,000 times the matter density, there will be practically no galaxies to talk about. And this is what, negative lambdas have to be handled separately, and I'll skip that. So this is the so-called entropic range. If lambda is within this range, you can have some structure, some galaxies. If lambda is beyond this range, no galaxies and no observers will exist. Okay. This, if you think of this as a prediction, this is a kind of prediction that is sort of guaranteed to be true. If you say that no observers will exist in this range, okay. This is, if you find that indeed lambda is in this range, this is not going to be terribly surprising. So to do better, we want to calculate the probability distribution, as I suggested. So we want to calculate the probability distribution for a typical observer to measure, or for randomly picked observer to measure a given value of lambda. And so let me outline how this can be done. So this probability P of lambda can be represented as a product of two factors. First, the volume factor, which gives you the fraction of volume in the universe, where lambda has a given value. And then the selection factor, which is the number of observers per unit volume for that value. So the product of the two gives you the number of observers who will measure this given value of lambda. Now, when you look at it, you can see that this is ridiculous to try to calculate something like that. Because of course, selection factor, how do we calculate the number of observers? We have no idea about how to quantify the evolution of life. And the volume distribution we might be able to calculate if we knew the details of the fundamental theory describing these transitions between bubbles and so forth. But now our theory, our understanding of that theory is pretty poor. However, in this particular case, and in a few other cases, you can make a lot of progress towards calculating this quantity. First, let us consider the volume distribution. So the volume distribution doesn't know anything about the observers, right? So this is a probability distribution, the P volume of lambda, which is defined in this huge range, ranging over 120 orders of magnitude. And Weinberg's entropic range, where observers can in principle exist, is very, very tiny compared to the full range of variation. So if you imagine any functions, so I do here any random function, any functions varying in a large range, and you look at this function in a very tiny range, then the function will look more or less like constant, simply because it doesn't have a chance to change much in this tiny interval. So on that basis, you can expect that this volume distribution in the relevant range, an entropic range where any observers can exist, can be well approximated by a constant. Now, what about the selection factor? The selection factor is the number of observers per unit volume. And what we assume here, so the claim is that this can be approximated roughly as being proportional to the fraction of matter clustered in galaxies. So if lambda is large, clustering stops early, and the fraction of matter that goes into galaxy is very small. If lambda is small, then galaxy formation goes on schedule. But the idea here is that lambda does not really affect life processes. So it only affects clustering of matter, gravitational clustering of matter. And if you have certain amount of mass clustered in galaxies, the number of stars per unit mass and the number of observers per star on average will be pretty much the same, because none of these things depends on vacuum energy. So this is the distribution that you find when you calculate according to this prescription. And you see it is peaked. This dark gray corresponds to 2 sigma. That is, this is the 95% confidence range. So you throw away 5% of this distribution total, or 2.5% on each side. And this light gray is 67%. This is the observed value. So you see that the observed value, it does pretty well. It gets in the 95% confidence range of the distribution. Now the distribution is small on large lambda because very little mass gets clustered in galaxies there, so there are practically no galaxies as you go in that direction. And the distribution is small at small lambda, because basically these small values of lambda correspond to unnecessary fine-tuning, right? So the range is very small, and to get into that range is unlikely and unnecessary, because basically the picture is that if you try to increase lambda, you increase it until to the point when it starts dominating at the end of galaxy formation. If you increase it further, lambda will start dominating earlier, and it will suppress galaxy formation. So the optimal value of lambda is when it dominates at towards the end of galaxy formation, not earlier and not later. Yeah, I should mention that this calculation was kind of improved as the data, as cosmological measurements were accumulating, but basically this calculation was made and prediction was made before the actual measurement of lambda. So it was a genuine prediction of the value of the cosmological constant. It was not a prediction of a pinned down value, but a prediction of a range, right? So here, if you want to make a prediction at 95% confidence level, this is it. If you want lower confidence, you make a narrower, you indicate a narrower range. So this explains the coincidence why lambda why the present time coincides with the end, more or less, with the end of galaxy formation epoch, for the reasons that I just mentioned. Also, I would say that this shows that the model can be falsified. Falsification is always at some confidence level, right? So if the actual value of lambda were beyond this range of 95% confidence, then you would be able to rule out the underlying theory at that confidence level. Finally, I think it's important to mention that there are no viable alternative explanations for why lambda is so small and why coincides with the method density. So I would argue that this is our first evidence for the multiples. This is not to say that the evidence is necessarily true. I mean, maybe that although there is some evidence theory, maybe that actually it is not the correct theory. But I think this should count as evidence for this multiverse picture. Well, sorry. Now, how much time I have? 10? Yeah, okay. So this kind of making predictions on anthropic grounds, this attracted some fire from various quarters. So here are some doubts that have been expressed. One is that some people argue that, okay, if you fix all other parameters, okay, you found this distribution for lambda, and it seems to fit, but what if some other parameters are varied? For example, Q here stands for the density fluctuation, amplitude of density fluctuations. If you increase this Q, galaxies form earlier, so this changes the whole picture. But this has been done. You can calculate the distribution, the probability distribution for combined for Q and lambda, and you find that the prediction is you don't predict the same value of lambda, but you predict the relation between lambda and Q. And the relation basically says what I said before, that lambda dominates near the end of epoch of galaxy. Now, Chris Smink criticized this approach because he says that this kind of is too general, because the kind of when we say that this probability distribution, volume distribution is a constant, and it applies kind of to any multiverse theory, so we cannot learn anything about that theory. I would say that we can learn something very significant, because this picture, we have a range of variation of lambda, as I said, is 120 orders of magnitude. And then if you have only a few vacua, there is no chance that these energy densities will get into the entropic range where observers can exist. So you have a you need a very dense spectrum of vacua, at least 10 to the 120, but you can improve on that. It should be much more. So in order for this entropic approach to apply, the theory should include a huge landscape of vacuum, more than 10 to the 120. And none of the grand unified theories qualifies. So it's only a string theory or some other theory with higher dimensions. And 1 or 2 higher dimensions are not enough. You need a substantial number, I would say more than 4. Also, people complained about this doesn't work like in particle physics. Like if you take, for example, the magnetic moment of the electron, which is given by this formula, and this number is calculated up to the 11th decimal point. And measurements were made with comparable accuracy, and the theorists are confident that if they do the calculation to the 12th point and do the measurements, there will still be agreement. Entropic predictions are not like that. For lambda, we have this probability distribution, and even if we calculate that distribution with very high accuracy, we would still have only a range, right? So that's the limitation that we will have to live with. However, notice that in some sense, this is a very sharp prediction, because if you think that your range, natural range of lambda is 120 orders of magnitude, and you make a prediction within a few orders of magnitude, so that corresponds to 100 of decimal points rather than 11. Okay, some other parameters could also be predicted and have been, like density of dark matter by these people. But for that, you need to specify what kind of dark matter you are talking about. So if dark matter is axion, which is one of the top candidates for the role of dark matter, then the prediction agrees with the, this is actually not a prediction, it's a post-prediction, but the model is pretty clean, so it agrees with observation. And another thing is neutrino masses. Notice that these parameters are singled out because dark matter is assumed to be neutral electrically, and neutral in the sense that it doesn't interact strongly with particles of the standard model. And similarly, neutrinos are very weakly interacting. So these parameters do not affect any physics relevant for life, but they do affect structure formation. So that's That's why they're useful targets for entropic explanations. Few minutes, okay. Now, I should mention a serious problem of this multiverse approach, and I would say of inflation theory in general, and this is the measure problem. So you have these bubbles which are continually formed, and the number of processes of any kind in this kind of universe is unlimited. So if you do some measurement, similar measurements have been and will be made in unlimited numbers. So if you want to predict the outcome of a measurement, if it is, let's say, a probabilistic quantum mechanical measurement, then you have to compare infinities. And that's inherently ambiguous task, comparing infinities. So you can define probabilities at a certain time, finite time. However, you discover that your answer depends on what you choose to call time. So you can imagine that you measure time by clocks of observers, which is called proper time, or you can, for example, instead of that, measure by how much the universe expanded, and you can use that parameter as time, and you get very different answers for some parameters. Fortunately, predictions for lambda are not sensitive to this choice, but this doesn't relieve us of the responsibility of addressing the problem in principle. So there were some attempts to, and this is called measure problem, meaning probability measure. So there were some attempts to derive the measure from fundamental theory, and they're interesting, but I wouldn't say that they are compelling. But I should say, well, personally, I'm pretty optimistic that this problem will be solved, that there is an answer, the answer, which is the correct measure, but we haven't reached it yet. Well, maybe since I don't have time, I'll skip parallels with Darwin's theory, and this is the summary. So I argued that the multiverse picture can be tested using the principle of mediocrity. This is one takeaway point, and the other takeaway point, if you're looking for a difficult problem to solve, I would suggest the measure problem.
Thank you very much, Professor Vilenkin, for the talk, interesting talk. And we will start we have about 10 minutes. So yeah, Yazan, I would ask you to come here and 15 minutes, okay.
Thank you for the talk. That was quite interesting. So my question is a bit more philosophical. So when you talked about the small range possible for the values of lambda, the very tiny range out of the all big range of probabilities. So my question, would you personally say that this is would lend its voice to a fine-tuning argument as some towards the existence of a higher power that made the range of possible lambda quite small?
Let's see. Let me make sure I understand the question. So you're saying that the small range of lambda that is necessary for the existence of observers, you could say that this could be the result of some sort of fine-tuning. Sure, but then you need the kind of the creator to choose somehow this value prior to the existence of observers. So sometimes you can explain fine-tuning by some physical processes, but here I agree with you that you could say, okay, lambda is what it is, basically, right? Or it is in this tiny range because that's the way it is. But I don't think this explanation is satisfactory. Am I addressing your question? I'm not sure. Well, I think the only viable explanation, it is not satisfactory for many people, but the only viable explanation that makes logical sense is the multiverse explanation. That lambda takes a large range of values, right? Most of them do not lead to the formation of observers, but some of them are in the entropic range, and this is where we find ourselves.
Second question. There are other questions, so maybe you can also. Okay.
Thank you. This goes in a similar direction. So when I came across multiverse theory first in philosophy of science, it was in order to give an alternative to design arguments and fine-tuning arguments. To arguments from design and fine-tuning arguments, so that we don't have to assume a deity, a god, something like this, but we have, so to say, the multiverse theory that just tells us intelligent beings, so to say, are possible in, it's very unlikely, but given that we have all this whole range of multiverses, it's such as one possibility that also occurred and was actualized like many others where it wasn't. But it sounded to me as if you were actually using the multiverse theory to answer a different question. So you introduced it in order to say, it's funny that, or there's this problem, why does lambda actually, so to say, have twice the method density? Why is it, so to say, so closely correlated? And in the way you seem to introduce multiverse theory is in order to answer that kind of problem, and that gives us this kind of range of when universes are possible. And these are two different questions. But then you introduced also, so to say, the anthropocentric viewpoint. And so I'm wondering, for you, does the multiverse theory actually answer the question of why is there, so to say, intelligent life, or does it answer the question, why is lambda, so to say, has the value it has?
Yeah, I think you are quite right that, well, first of all, I think I may not sufficiently emphasize that in order to make anthropic predictions, at least in the way I understand them, you need a model, right? It's not like you say, okay, every universe, every kind of bubble is possible, and you just let your imagination go. You have a model, right? For example, like string theory. It's not easy to do calculation with, but something you can say about it. And in the framework of that model, you do the calculation of probabilities. And it's lucky, maybe it's a lucky thing that in the case of lambda, the details of the model are not very important, other than the existence of a huge number of different vectors with different values. So in this case, in this sense, you use the model, you made the prediction, and yeah, so am I drifting away from your question? No, this has nothing to do with, the only thing I used about the intelligence is that lambda has no effect on the evolution of intelligent life. right? So I'm saying that I'm comparing different bubbles, and I have no idea how long it takes for intelligent life to evolve. But if the physics in these bubbles is the same, other than lambda, is the same as here, right? So we can expect that the life will evolve more or less like in our region. And the only difference between this set of bubbles will be that structure formation will go differently. Where lambda is large, it will be suppressed. Where lambda is small, it will not be. And that's how we calculate this probability distribution. Have I addressed your question? I'm not sure that. Okay, please do.
There is another question.
Thank you very much for your talk. So you introduced this probability distribution, and you said that this is like a falsifiable model, something like that. But have the worry that what is the thing that is being falsified? Is it the multiverse hypothesis or your string theory or whatever, or is it the second component that entered into the discussion? Because you have the second component, which was how many observers do you expect it to have it for different values of lambda. So this is what is giving you like most of the shape, because as you were saying that the probability distribution for lambda in this range was like pretty flat. So my worry is that what we are falsifying is our beliefs about how many galaxies do we expect to have if we have this value of lambda. So
Well, I don't think I assumed anything about the, let's go to this plot. Yeah, or maybe even here. I don't think I assumed anything about the number of observers. Basically, what I said is that the selection factor is the number of observers, right? And all I said was that I assume that the number of observers is proportional to the number of galaxies. And the number of observers per galaxy, I assume to be the same in a bubble with the same kind of physics, right? And I think this is a reasonable assumption. And
so yeah, like there are two components in this probability distribution: your hypothesis about the multiverse of string theory and everything else, and the second part, like how many observers there are. So my question is, what is the part that is being tested? If we are like looking at lambda, like to me it seems that what we are testing is the second part, because the other thing is pretty flat and it doesn't get much information. So it's, for me, it doesn't feel that surprising that lambda is inside the observable range.
well, let's see. So we are not, what is we are testing, it's a good question. We are not really testing this volume distribution, because for a wide range of models it will be constant, right? So let's forget about that. So here, if we have a model which gives us a huge number of vacua, right? Then I think it's also reasonable to say that the second factor will be proportional to the number of galaxies per unit volume. So then the question is, do we really live in a multiverse with a huge number of vacua? And I think this is what we are testing.
Thank you for questions. If there are no other questions, I think we can. Sylvia, there's. Sylvia, we cannot hear you. The comparison that you skipped.
Comparison. Oh, you comparison with Darwin. Okay. Yeah, I wanted to close this by drawing some parallels between the theory of evolution, Darwin's theory of evolution, and theory of inflation. First of all, both theories were proposed to explain something that was not previously believed to be explainable. Right? With Darwin's evolution, obviously the origin of species, and in the theory of inflation is the initial conditions. So when I gave talks about theory of initial conditions, one of my friends, Lawrence Krauss, after the talk, came up to me and said, to give such a talk and survive, this is incredible. So in physics, talking about initial conditions was not considered a kosher thing to do. In both cases, the explanation was very compelling. I can support this claim for the theory of inflation. No viable alternatives have been suggested, and this is not for the lack of trying. There were a number of attempts to suggest alternatives to inflation, but I would say they are not nearly as convincing. And so the Darwin's theory was widely accepted, even though some important aspects remained unclear before the discovery of genetics. And finally, I made a point that the theory of inflation is similarly incomplete and may require new ideas. I would say that as it stands, it is already quite a successful theory. So if you limit your range of questions, you get very good agreement with the data. No, okay.
Thank you, Professor Vilenkin, for the talk. Thank you, everybody, for coming.